So once again, my name is Georg Pimpel. I work in the kite engineering department of SkySails, along with Paul Tedens, who's also here in the room with us, and our team lead, Mary Moda. And today I'm here to tell you something about how we multiplied our average power output over the past year and a half, or more specifically, how we managed to reconcile our roll steering technology with fast depowering capacity. So to give you a quick look at the agenda, I will first briefly introduce you to our power system. I will then tell you something about the obstacles that we faced towards the end of 221 and how they led up to the development of a variable pitch power kite system. And you will see that this is all going to be much less theoretical than many of the talks you've seen at this conference. But if you bear with me, then I'll present you with some aerodynamic performance data and some optimized trajectories and power cycle analyses towards the end. So, to get started, our currently marketed system is called the PN14. As you can see, it's a ground generator based soft ram air kite power system. Our kite is actually much closer to a paragliding canopy than to the tube kites that you use for kite surfing. Right below it sits the control pod, which connects to our ground station via an 800-meter long tether. That ground station sits on a tripod with a ring mount and houses our winch, which connects to a generator and several other electric components. Now, before I can go into the advances that we made with our kite technology, I first need to tell you a bit about where we were coming from. And as some of you might know, SkySails was already founded back in 2002 with the original intent of not harnessing airborne wind, but of pulling off large offshore vessels. So for the 10 years that followed, a lot of effort was put into perfecting kites that were robust, had a wide operating range, had great starting and landing capability, and were well suited for roll steering. And roll steering is a technology that we have patented for a long time, which stands out because it's great maneuverability and because it's highly energy efficient. And because it's very relevant to this presentation, I'm just going to briefly explain it. You can see an illustration of our roll steering principle here on the bottom right, and at the heart of it is a roll steering belt, which goes through the control pod and connects both of the tips with each other. And now if you deflect that steering belt, and you pull one tip in closer while veering the other away, and that creates, or that shifts your aerodynamic force vector to the side, which puts you into a turning maneuver. Yeah, and obviously when we shifted to Airborne Wind Energy a few years ago, a large part of our kite technology and our pod was transferred to our new system. But there's one disadvantage that I haven't talked about yet, which is that the old kite was designed for a set trim angle of attack. And that made sense because we wanted a kite that was good at doing what it should, which was pulling very strongly and flying very quickly. And aerodynamically speaking, this reflects in some constant aerodynamic loading coefficient and a constant glide ratio. Now, moving on to airborne wind, the consequence for us was that because we had a kite with constant aerodynamic properties, we couldn't change our value of CR or our glide ratio. We had to fly very long trajectories to maximize our net energy gain. And this traditional pumping cycle, many of you will have seen before. So the first phase is always the power phase. You fly the kite in figures of 8 through the high force zone of your wind window. And once you reach your final tether length, you put it into a transfer trajectory to the low force zone of the wind window, where you then reel it back in. And as you may have guessed, those second and third phases are quite unsexy, because that second phase is simply time consuming. There's a long arc length that you have to cover from the high force zone to the low force zone of your wind window. And the return phase is time consuming because your large glide ratio that you can't change limits you in your reeling speed, because if you were reeling the tether too quickly, then the kite would overshoot and crash into the ground behind you. And it's also energy consuming because the kite is still trying to pull as hard as it can on the tether with the wind that it has. So now what if we could skip the transfer phase and reel the kite in right in the middle of the wind window with almost no loading? That's possible, but in order to do that, you have to significantly reduce your value of CR and your glide ratio for that reeling phase. And yeah, for us, this meant that in the end of 2021, we decided that we needed to redesign our kite and our bridle to set that stage to meet our future energy targets. So the objective was quite clear. We needed to find a way to reduce our aerodynamic resultant loading coefficient, CR, and the glide ratio to values of about 0.1 and 1 respectively for that return phase. So that's this arrow from the right. This is where we want to reduce power, and this is where we want to reel it in. And there's an obvious way to do this aerodynamically. You have to change the pitch angle, you have to reduce the pitch angle of your kite. So if you move from the right to the left, you lower your angle of attack, then you significantly reduce your CR and your glide ratio to a point where they almost go to 0. But you can't directly change the pitch angle of the kite. What you can do, though, is change its trim state. And this is illustrated here on the right. So changing the trim of the kite means basically rotating the control pod along the longitudinal axis of your, or along the x-axis basically of your coordinate system, here to the left. And that effectively lowers your angle of attack on the kite. And I know many of you will think, well, that's nothing new. Like, kites have variable pitch systems, or can be trimmed. But I think our system stands out for 2 reasons. One is that this range that we can now trim is extremely large. We can rotate the pod by around 40 to 50 degrees around our canopy. And 2, pre-existing trim systems will typically rotate around the leading edge of the kite by either reeling in the lines behind it closer or veering them further away. We chose to rotate about a more neutral lap plane. In this schematic, it's the middle one, where in order to change the trim, you will move the lines in front and behind that point of rotation in opposite directions, which for your actuator means that it only has to overcome the differential force between them. So that's quite similar to our roll steering technology, where we also just have to overcome the differential force. And now you're taking a look at our first prototype. These are pictures from, I believe it was April last year. It ended up being very successful, but I'll get to that in a second, and in other respects not so much. In the beginning, we didn't know how to reconcile our beloved roll steering mechanism with this depower mechanism. But we thought we didn't have to, because with this capacity to change the trim angle of the kite, we thought it might make sense to switch to torsion control. And this is very well illustrated here, I think. What we basically had is one trim system for the port side, one for the starboard side, and then if you would implement an asymmetric trim, that would induce a yaw moment around your tether that would shift you around the corner. So much for the theory. And as I said, this worked very well for us with some respects. In April last year, for the first time, we were able to depower our kite to CR values of about 0.1 and glide ratios of 1, which was great. We didn't even know if this was possible before we started. But it also turned out that there were some heavy disadvantages to torsion control. The first being that it requires relatively large values of the A, of the apparent wind at the kite, to work well. It had bad turn rates, even when everything was matched up perfectly. Asymmetric, it works on the basis of asymmetric drag, so you increase the drag on one side, you lower it on the other, and that's what brings you around the corner. But that also means that your average glide ratio will suffer from it, which is bad for your overall performance. And then lastly, for this to work, we had to constantly actuate our trim actuators, which is very energy consuming in the long run. So bad for the energy balance of the energy self-sufficient control pod. Now, how do we get back to joining the best of both sides. We had a system before that was very good at steering with our roll steering system, and now we had a system that was very good at depowering. So how do we join the two? As I said in the beginning, we didn't know how to, but then after, I think it was May last year, we came up with this concept where you can see both a roll steering mechanism on the bottom and our trim actuator on the top. And effectively what we do is we have an intricate pulley system in our bridle that modulates deflections of either one to the canopy, so that we can both implement a roll deflection and it will be felt at your tip just like the trim. And as I said, we've now patented this, so I can safely present this to you. So this worked very, very well. It's very fun to work with. So we now have the same depower range as with the torsion steering. We only have to actuate the trim when necessary, so that is when switching from the power phase to our return phase. In all states in between, we can just put a brake to the actuator and it just sits there. So that's very, very, so in that phase, it's basically the same amount of energy that we use as before. There's a huge design space for fine-tuning. So all these pulleys and lines and opening angles give you a lot of, lot of space for thought and for perfecting this the mechanisms. Yeah, and thanks to the roll steering principle, we now went back to a kite with great maneuverability and high energy efficiency. So this is a picture from last month, I believe. Obviously, we've done extensive tests with this now. We've scaled it up to our largest kite systems too. And yeah, we're slowly but surely getting used to it and getting it out on the field. Now, I promised I would show some data as well. So these are some measurement data we collected in a flight test in April. What you can see on the left is our CR value over trim, on the right is the E over trim. We normalized CR just for, I don't know, it's still industry, right? So as you can tell, we lower our CR by about 85%, going from our power state to our depowered state. And we are now able to lower our glide ratio from a power configuration of 7 to virtually 1, right? So feels very good after having worked in it for such a long time. It's very satisfying. What you can see here is a look at a cycle comparison that was done using Kasadi. I'm not the expert on this, it's a colleague's, but it's basically nonlinear optimization on, what was it? It's an optimization algorithm. But what you can tell, obviously, right, is that with our new depowering configuration, we can cut the return phase by a large margin because we can reel in at much faster speeds and at much lower values of bar theta, so the kite stays way further inside the wind window. So all in all, we can just reduce this unsexy time where we don't use a lot of energy, spend a lot of time on, to an absolute minimum. And yeah, so this, in this case, this was done at 12 meters per second. Kasadi predicts that the power increase is of about 2.4. This is the same cycles, only visualized. And the only key thing to take away from here is that on the left we have the old configuration without a depower mode, where, again, this is the optimal, right? This is the optimized case. The optimized case would take the kite basically behind the ground station as far as it could before reaching its limit, basically, resulting in a much longer trajectory and lower reeling speeds. Whereas now we can basically reel in the kite at almost 45-degree angles. And go straight back into the production phase. And I didn't take a look at the time, but I already checked that the video didn't work. So I prepared myself with a backup. This is a video of 2 cycles. It's sped up to a factor of 4, so don't be confused why the wind turbines are spinning so quickly. There's even some audio if you want to. But you couldn't hear much anyways. But yeah, so now the kite is returning from its return phase, and we'll go into a dive soon. Getting started again on its.
How large is the kite? Just
how large?
This
is 110. Yeah, so now it's just finished its production phase, its power phase, right? So this is the return trajectory, and now you will see it going to a dive real soon again. By the way, these are real-in speeds of about 13 meters per second on the winch.
30?
So 13. But yesterday we had a test where we went up to 15 with a 180 square meter kite. So we're really only limited anymore by the speed of our winch and not by the kite. Yeah, so this could go on forever, obviously, but all the following ones will look the same. That brings me to the end of the presentation. So I would like to take any questions if you have some.
Are there any questions? Maybe just a quick question for myself. Did your master thesis that you did in a TU Delft wind tunnel, I understand, was about this aerodynamic brake, destroy lift? Was that a successful concept in the end? Was that implemented or on a real wing?
So what you're talking about is a CFD study that I did for my master thesis.
Yeah.
And there I investigated the use of bleed air spoilers to lower as well the CR and the glide ratio of the kite. And what my results showed was that it was really difficult to use bleed air spoilers to do something about the CR, but then it was very effective for the glide ratio. But in the end, we knew that that alone wouldn't be enough to get us to this point. So, so we just went straight to the pitching.
Okay.
But yeah, I mean, it went along with the power increase of 30% as well, according to the calculations, but it wasn't 240%. Yeah.
Okay, so maybe maybe you said it already. So average power output changed by how much by this change?
I mean, I can't show you our actual power curves.
No,
but I mean, in this case, it was factor 2.4, right? And the one, like the 2 power cycles that I showed, these 2, right? This was a factor of 2.4 at 12 meters per second on the bottom right, top right.
2.4 more power.
Ah, yeah, okay, my bad. This was supposed to say P nu is approximately equal to 2.4 times P old, not P nu.
Okay.
So that's just because you're able to fit in so many more cycles into a given time window, right?
But the time is more than half of the old one.
The old one was about 250, and now we're down to 150.
Yeah. So you should fit, if they give the same power, to say you get the same power per cycle, you should fit 2.4 of the new ones in the old one, or am I getting something?
But you're also spending less energy, for instance, on the reeling phase here, right? Because your CR value is so much lower. So this is the reduction. The time-wise reduction is due to your lower glide ratio, and then there's also the CR that comes into play.
Isn't also the difference that the percentage of time that you're producing during a cycle is much increased?
Exactly. Yeah. So that's the two effects. What you can see here is that added benefit because of the time, and then what you can't see is the CR.
Hi, Christian from Airborne Europe. So that one was my question. What is now the time ratio between power cycle and then turning back? Is it these 20% you need to get back?
I mean, in this case, right, we're looking at about 90 seconds, 80 seconds production, and then another 70 for the reeling. Well, I guess you could say you're still reeling out until this point. So it's about 2 to 1.
Okay, thanks. And the other question, that it would take long with this previous concept, why, or you must have known that for a long time, and then why did it come like only 2021 to say, okay, now we have to change something. Or you had to test that long to really see that it doesn't work with the old configuration.
We went into a lot of risk to go this way, right? And we had a kite system before that served us very well, and we would have been able to meet our next 2, maybe 3 targets with that system, but we knew that it wasn't setting us up for the long run, and then it just made sense to take the step.
Of course, at TU Delft and Kite Power, we had already like 13 years invested into this concept with a lot of success. So we also have this pitch control and the roll and twist steering.
Yeah. But I think it's important to point out that there is major differences between your approach and ours, right? Because in your case, you're just actuating the lines connected to the trailing edge.
Yeah.
Where we are now actuating all the lines from the leading edge to the trailing edge, and we're modeling that roll effect on top of the trim state.
Yeah.
The two are separate.
We have not seen the SkySails concept except here now.
Yeah.
So of course we will definitely look at the details.
Just keep this in mind.
No, thank you for the presentation. I was indeed a little bit of a follow-up on the question on the graph. You already mentioned you cannot give us the real power curve, and I get that, but I was wondering, like, I guess you're now comparing both of the simulations with each other, right? So the causality optimization, but it's both simulation. So you have 240% increase on your simulation, and we also know pretty much always currently with prototypes we're not actually living up to what we're simulating.
Oh, actually, we're exceeding the simulations.
But you're expecting, in this case, that would you expect the same 240% increase, or would you indeed think it would be lower or more, as you said now?
No, we're at the moment exceeding the simulations because we're simply having so many safety factors in the simulations to account for steady winds, for instance, and all those things that we can often do better.
Okay, thank you.
Any other question? Maybe one? Well, 2.
Hey, thank you very much for the presentation. I was wondering, you said you're trimming in all the bridle lines. Is that true, or just the one in the front and one in the back and then one in the middle stay constant length?
There are more lap planes than just the 3 pictured in this schematic. So right now we're working with somewhere between 4 and 5, for instance. And then, right now we're rotating on the B plane. There's 1 plane that's in front and 2 to 3 planes behind. And that's just pulley systems in the end.
Okay, clear. Thanks.
Yeah, thanks. So the added complexity of the control pod now, did it, like, say, I don't know, double the mass, and did it make the whole control architecture and being sort of fault tolerant and everything a lot more complex? Can you say something about that?
I mean, it goes without saying, obviously, right, that there were a lot of people involved in this, and we're not at the end of the line yet. We have everything working well, but we're still working with prototypes. So the next iteration is going to be one that we can hopefully roll out to the field as well. But yes, I mean, the added, the added amount of actuators inside all these things, larger batteries, that adds to the weight.
Thanks.
Thank you very much again.